So in many applications, relations between an n vector and an m vector are either approximated. Sometimes the approximation is very good, as linear or affine, right? So sometimes the approximation is really good and holds over, like, holds out at the, fifth and sixth decimal place or something. An example of that would be electromagnetics or, for example, acoustics. There are many cases where it's just like that function is basically linear. Now, sometimes the approximation is just, it's pretty good over smaller ranges. So for example, aircraft dynamics, right? If I take an airplane and I ask what are the forces and torques that are put on the airplane, as a function of its speed and sort of the angle of it, the angle of attack and the control surface deflections, that's approximately fine for reasonable ranges. Certainly for most of the ranges that you would be comfortable flying in an airplane in. But it doesn't hold when the airplane is like falling out of the sky or upside down or something like that. Okay. Now in other cases, still the approximation is quite approximate, like it's plus minus 50% or worse. But it's still super useful. So that's, for example, in econometric models, right? So I mean, just to put something on this, my colleagues in electrical engineering, when they're doing E&M, their models, they can predict things to 3 significant figures quite easily, right? So that's good. My friends who work at hedge funds, they basically put it this way. They say, we're happy if we get the sign right, okay? So, but nevertheless, it's still useful. Okay, so our first example is from economics. So here we have n goods or services. I'll just imagine them to be n goods. And we have the prices for those goods, the market prices, are given by an n vector p here. So p3 is the current price of item or good 3. And we have demand, and that's given as an n vector d. So d4 is the demand, the number of units of good 4. Okay. And then what you do is what we're going to do is we're going to imagine changing the prices. And so what we do is we take the new price, that's pi new, that's the new price for item or good I, minus pi. So if that's positive, it's a price increase. If it's negative, it's a decrease. And we divide by pi. Oh, the prices, I should say, are all positive. Okay, and that has a beautiful interpretation as the fractional change in prices. And we're going to call that delta price sub I, right? So if that is equal to plus 0.1, that means basically you just increase the price of that item by 10%, right? If it's minus 0.05, that means you just decrease the price on that item by 5%. Okay, so highly interpretable. So that's what the delta vector gives you. Delta price vector, it tells you the fractional changes in the prices for those goods. Okay, now we do the same with demand, right? We have the fractional change in demand, right? So if we subtract from the new demand, we subtract the current demand or something like that. We divide by the current demand. And demand also, by the way, is positive. And so this is the fractional change in the demands, right? So that's how that's the idea. So for example, if delta dem sub 2 is minus 0.1, that says that the change in demand for good or item 2 went down 10%. So highly interpretable. Okay, now clearly there's some relation between the prices and the demands. We all know that if you have a single thing and you increase the price, the demand goes down, okay? And what relates them is called elasticity. The elasticity, in fact, that's called the price-demand elasticity. And for multiple goods, there's a very common model, and it looks like this. It says that the vector of demands is a matrix E called the Elasticity Matrix times the relative changes in prices, delta price. Okay. Now that's super interesting. E is an n by n matrix. It's called the Elasticity Matrix, and it's highly interpretable, and it's very important to understand like what it means. So, for example, E11 is minus 0.3. What does that mean? Well, E11 tells you how much does the price of the first entry tells you, how much does the demand, that's the first one, so we say 1, how much does the demand for item 1 change per fractional change in the price of item 1? And this says minus 0.3, and so here's a specific, this is a very specific conclusion. This says if you increase the price by 10, let's make it less, like let's increase it by 1%, right? If we increase the price for item 1 or good 1 by 10%, our model, the price demand elasticity model, predicts that the demand will go down by 0.3%. Okay, so that's what it says. Oh, you can ask another question. Does your profit go up or down? And that depends on how much it costs you to manufacture and all that sort of stuff. So we're just predicting how the demand is going to change. Of course, people are interested in how the demand is going to change for two reasons. Number one, for supply chain, you want to make sure you can actually have that amount of that good on hand. And the other thing is you want to find out what happens to your profit. Does it go up or down? Okay, so all right. E12 equals plus 0.1. Super interesting. Let's see what it says. That says that under the price demand elasticity model, if you increase the price of good 2 by, let's say, 1%, this says you can expect the demand for good number 1 to go up by 0.1%. So increasing the price of the second good increases the demand of the first good. Now, that comes up all the time. And what people call, but in economics, these are referred to as substitutes, right? That, that somehow if people say, oh, that's more expensive, I'm buying less of it, right? So that would be E22, is minus, 0.2 or something, right? So if you increase the price, it says that the demand for good 2 goes down, but the demand for good 1 goes up because they're substitutes, right? So that's the idea. Here's one. E23 was minus 0.05. That tells you that if you increase the price of good 5, it says that the demand for good 2 goes down. And if you increase the price for good 3, then the demand for good 2 goes down. And it's quite specific about how much it goes down. It's not much, right? But it's so what that usually says that, the typical thing would be if you increase the price for shoes, of course the demand for shoes goes down, but also the demand for socks goes down or something like that. Okay, so, and there's a name for that in economics, which I've forgotten, but this is the idea. But it's a very, very common model. Of course, it's only accurate for small changes, right? If I double or triple the price, I would hardly expect this thing, this simple model, this simple linear model to hold. But for small changes, it's actually pretty good. So it's a pretty good way to predict stuff. Okay. The next one is another source of affine models is directly from, well, differential calculus. In fact, you can even say that differential calculus is nothing more than an organized way to come up with an affine approximation of a function given by a formula, so you can, do all your derivatives and stuff. Okay, so here the setting is, suppose that we have a function from Rn to Rm, and it's differentiable, okay? And the first order Taylor expansion of f hat is called f hat of f near z is equal to this. It is equal to, now, to tell you what my approximation is, I have to tell you what each of its component is. So I'm telling you what the ith component is. It's f hat I of x is equal to fi of z, that's the value of f at z, plus, and then I have a whole bunch of little terms here. Each tells you about how much you've changed x from z, and then you multiply by the associated partial derivative. So that's just the Taylor expansion, and you've seen that before, and that we write out this way. In fact, we've seen this in previous lectures. It's an interpretation of the inner product. So it says that fi hat of x is fi hat of z plus the gradient of fi at z inner product with x minus z. Okay, which is, and x minus z is interpreted as the deviation of x from z. Okay, and in compact notation, people write that this way. F hat of x equals f of z plus df of z times x minus z. Okay, now df is an m by n, it's called a derivative matrix, Jacobian matrix. It's got other names depending on the field, right? And in some cases, it's very specific, right? It's about, it's got all sorts of names, like, depending on the field for specific applications. But here, it's called the derivative or the Jacobian matrix, and it's a very simple, thing. It looks like that. It says that, roughly speaking, it says your approximation is the value at z. Now, these are all m vectors. It's the value at z plus an m by n matrix times your deviation from z on your input, right? So that's kind of the idea. And this thing, you can think of it this way. This derivative matrix has rows, which are the transposes of the gradients of the entries of f. Or you could think about this, that this is a matrix, and to get its ij entry, you take the partial derivative of fi with respect to xj, and that's what it is. So another way to say it is df of x is the matrix. Actually, this should be a z here. Sorry about that. It says that it is the matrix of partial derivatives is what this matrix is. Okay. And the idea is that that is a very good approximation of x for x near z. And it's an affine function. So, it's not clear it's an affine function. Well, I think it is. We could write it this way. We could write it as df of z times x. That's sort of like the ax. And then the b term looks like this. I'll put it together. It's f of z minus df of z transpose z, like that. Okay, so this is sort of like a, and this thing here is sort of like b in the way you write it, an affine function out. Okay, so this is a giant source of affine functions. It's simply, you do a first order Taylor series expansion of your function, and that's going to give you an affine function. Another one where it comes up is in statistics, machine learning, and prediction. So, and it's called a regression model. You've already seen this before, but it's worth, here we can actually stack it into some vectors, and I'll explain how that works. Okay, so the regression model, remember, looks like this. It's y hat equals x transpose beta, or the inner product of x and beta, plus v. Okay, now here, x is an n vector of features, or regressors. Depends, so these could be attributes of a patient or anything else, attributes of a person or a customer or of an email or something like that. It doesn't matter. So that's what x is. Beta is an n vector of model parameters, and v is the so-called offset parameter. And then this produces a scalar y hat. And that's our prediction. Remember that a hat on top of something is not universal, but common mathematical, is certainly in applied math. It hints that it's an approximation of something. And in this case, it's an approximation of y. Y, we assume, is what the actual observed value was. Now suppose that we have a so-called data set. And a data set is going to be, we have a set of, we have capital N samples, and x1 up to xn. Those are vectors, right? And then I have the associated responses, and those are y1 through yn. Okay. Now, these are just like some observed. It's a data set. It's observed data. Now we can also, for each of the x1 through xn, for each of our data, our observed or data sample features, we can actually calculate what the prediction is. Y hat I is this. Now, it's clear, a super good predicting. What we really want, of course, is this. We want y hat I to be approximately equal to y of I, like that. So that's what we'd want. If they're close, then we'd say that your model does a very good job predicting y. That's the idea. Okay, so what we'll do is we're going to stack we're going to stack our data set. We're going to form a matrix and a vector out of it. So what I'll do is I'll form a vector y hat d. D is for data, and it simply stacks the observed y's on top of each other. It's a capital N vector, and I'll make a feature matrix with the columns x1 up to xn. By the way, it's also very common, in fact, honestly, it's more common in statistics to work with the transpose of x, but you just have to figure that out. When you go to your internship and someone says, here's the data matrix, you have to figure out, are they talking about, are the columns the features or are the rows? And while in this book, we make the columns the features, it's probably more common on the streets for people to give a data matrix with the rows, but that's fine. And I'll show you why that is in a minute. So the reason is when you write down a matrix vector notation, you write this, that the vector of predictions is the data matrix transpose times beta, that's a vector, plus v times the vector of ones. Okay, so now you can see why people often work with the data matrix having the rows as the features, because then you don't have this transpose here before the matrix vector multiplication. But it's fine, that's the idea. And so, for example, the prediction error, and it's a vector, is yd minus y hat. It's what actually happened minus, and then your prediction of it, and that's going to be equal to this thing. And so, for example, if I take the RMS value of the prediction error, and it's 0.1, I could say, ooh, on that data set, my regression model made predictions that were about, plus or minus 0.1. I mean, that's what it means to have an RMS value of about 0.1. So that's the regression model. We're going to see a whole lot more about that later in the class. So far, we haven't told you how do you find beta or v. We'll see that later in the class. It's a very important thing. But for now, we can certainly interpret and look at a regression model before you know how to fit one. Fitting one is going to come later.